Example 4-1 is about a 2-meter wide rectangular channel which carries water at 20 degrees centigrade at a depth of 0.5 meter. The channel has a slope of 0.0004 and is made of concrete with a surface roughness of epsilon equal to 3.5 millimeter. So the question asks to find the hydrodynamic nature of the surface and estimate the discharge of the channel using the Shesi formula. So in order to determine the hydrodynamic nature of the surface, we need to calculate bed Reynolds number and determine whether the bed Reynolds number is less than 4, between 4 and 100, or more than 100. So I do the sketch of the channel cross section and longitudinal direction of the flow with the depth and roughness. So the Reynolds number at the surface is equal to the length scale, which is the roughness, multiplied by the shear velocity, which is the square root of shear stress divided by density, and divided by kinematic viscosity, which for water at 20 degrees centigrade is 10 to the power of -6 meters squared per second. So the shear stress is equal to rho g RS0. So we have a density of water, 1000 multiplied by 9.81. Hydraulic radius can be calculated easily for rectangular cross section. So we have R equal to A over P. A is the area, cross-sectional area, divided by wetted parameter. So we put the value of 1/3 meter here, multiplied by the slope. So it gives me 1.308 Pascal. Then from that, I can calculate the shear velocity, square root of shear stress divided by density. So the shear velocity or the velocity scale at the bed is 3.6 centimeter per second. And then I can calculate bed Reynolds number, which is epsilon 0.0035 meter multiplied by 0.036 meter per second, divided by 10 to the power of -6 meters squared per second. So here we have 126.58, which is larger than 100. So we are in the classification of hydraulically rough surface. So for hydraulically rough surfaces, you can find the formula for Shesi equation from the textbook. So we have the Shesi equation equal to 28.6 multiplied by the Reynolds number to the power of 1/8 if Reynolds number is less than 10 to the power of 5. If it's larger than 10 to the power of 5, then we have the second equation. So in this case, we are going to use Excel. So I developed the Excel sheet here. So we have the epsilon, the roughness, hydraulic radius, longitudinal slope, and this is new kinematic viscosity. So assume that hydraulic radius is less than or equal to 10 to the power of 5. So we use the first equation, which is 28.6 times Reynolds number, which is 10 to the power of 5 to the power of 1/8. So that gives me a Shesi coefficient of 120. From that, I can calculate velocity, which is Shesi constant, the square root of RS0. So that gives me the velocity of the flow. And now I have velocity, I can calculate Reynolds number. So Reynolds number is 4R, 4 times of hydraulic radius, multiplied by velocity, divided by kinematic viscosity. So here you see that our boundary was 10 to the power of 5. What we get here is 1.86 10 to the power of 6. So it means that we cannot use the estimated discharge here because the formula that we use is for Reynolds number less than 10 to the power of 5. Therefore, we are going to use the new or the other formula, which is 4 times the square root of 2g times log of Reynolds number times 8g to the square root divided by 2.51 times c. Okay, so we can do try and error to find this value. So what we do is we just put the value of 100 here, and then we get the value here. So let's say if I put 100 here as a start, so I got 85.3. Then I put 85.3 here. I got 86.6. Then I put 86.6. Then I get 86.4. So you see that it converges to 86. So 86.5. So I inserted 86.5 and I got 86.5. So it converges. Then I calculate velocity based on the calculated Chezy coefficient, calculate Reynolds number. So here we have Reynolds number, 4r times velocity. And from that, we calculate discharge, okay? So the discharge is velocity times area, width times depth times velocity. Then we got a new value of Reynolds number. So you see here we have, we need to use in Chezy calculation of Chezy equation, we should use Reynolds number. So now we got the new value of Reynolds number. So what I need to do here, I just need to grab this, and then I need to update Reynolds number with a new value of Reynolds number, which is already updated. Okay, so now you'll see that it's different. So 83.9, I need to first fix this, 83.9. So I got 84.1, 84.1. So it's converged. So I put 84.1 and I got 84.1. Then I calculate velocity with the new updated Chezy coefficient. And then I calculate the new Reynolds number. So you'll see that we got the new value of Reynolds number here based on velocity and a new discharge. Okay, so then in the next step, we'll go based on the new Reynolds number. We calculated new Chezy coefficient. So now here we have a new Reynolds number. So it's 83.9. So I need to put here 83. So you'll see we have two optimization. One is internal optimization to calculate the value of Chezy constant. So 83.9 here, 83.9. You see in the first shot it optimized. Then I calculate velocity and Reynolds number. So you'll see Reynolds number is also converges. So at the beginning, using the new equation, we have 1.33. Then it's become 1.29 and then 1.29. And then I can just do another update, 83.9. So doesn't need any change. Maybe a slightly change here. Nope. Yeah, so basically we got, so what I can do is I can just change this format cell to maybe with 4. Yes, gives you a better idea that the value here are not exactly, so this is 83.897. The previous one was 83.914. So you'll see that we had a slightly better value. I can also change this one into 83.897. Yeah. And that would be the final value of discharge based on try and error.